Thanks, everyone. This is Zoe from Visionular. So as you can see from my title, basically for this talk, we just want to present some of the pursuits we have been working on, mainly leveraging, because everybody is talking about AIs, for video compression. But there's two parts of it. One is the traditional video compression. We try to save the bit rate. And then so that we can further actually save the sitting cost. On the other side, because a lot of videos are being processed by large models, so we're also talking about token compression. And that's actually for the use of definitely saving the compute cost. So that's also my talk will actually divide into two parts. This is actually the work that we have been collaborating with NVIDIA. So you can see that this is silencing detection. It's well known that if we identify the region of interest, then we can actually put more bits into those regions. And then for the rest of the things, if possible, we can put less bits. So this is where we can definitely save more bits. But then for this one, if we're actually doing the traditional video compression for human eyes, we have to be consider whether the final video will actually make amenable to our human eyes, because this is different. However, many videos right now, you also compress it using a traditional way, but finally be absorbed by AI models. So if the AI model take it, maybe you can actually put a background and plus the foreground as well as the temporal domain information into that model. So you actually can save a lot of bits using still the traditional video codec, either MPEG codec or LM codec. So this is we want to see that there's some salient features that we can actually detect, but how to detect it, we can use lightweight AI models before feeding these videos into a traditional video encoder. And then, so that's why nowadays, when we talk about traditional video compression, it's actually classified into two categories. One is that actually the video compression for bitrate savings, but for human eyes consumption. And the other side is actually for the AI models, where we can talk about machine-based video compression. So there's quite some things at least down there. So just now when we talk about colors, when human eyes observed videos, they really care about whether the color is colorful, is actually fit out to the real world. But when models, AI models observe it, for example, if I identify the traffic light, you only just care about whether it's red, green, or yellow. You don't really care about whether this yellow is actually genuine yellow or some other colors. So there's a lot of things you can compress because finally the models will be fed. Finally, the compressed videos will be fed in the AI models. That's why I list down here is also talk about, for example, some features, frames, and then essential things. As long as you actually preserve it and the models is good enough to actually identify what the model is supposed to be, that information is good enough. So now we can see that the video compression, even for the bitrate savings, for different purposes, for human-oriented, are very different for machine-oriented. So there's a slide talking about the two codec standards. One is MPEG, the other is LM. I want to specifically mention that just yesterday, July 28th, the Tuesday, they actually have a new it has been going on for a while. It's actually called Video Coding for Machine. It's actually a new effort. Yesterday, they actually finally got this CD confirmed, and the final proposal is being called. So this is a stage that the standardization organization is already called for proposal for next generation standard. It's actually targeted for the machines to absorb. And then on the other side, you see the LM side. I just want to talk about some existing codecs, like everybody knows about AV1 and AV2 just announced 1 month ago. Particularly, there's one feature preserved by AOM. It's actually mentioned that screen content coding. And screen coding is actually was very hot during the pandemic because when we do video conferencing, no matter Teams, like Google Meet or Zoom, and WebEx, we all know that we have screens for presenting the slides, sharing our screens. It's actually AV1 contains screen coding tools. Short as SCC is very efficient at coding those screen content. However, if you think that screen content, you can actually generalize for gaming, for even AI-generated content. So you can actually classify this as computer-generated content. When you actually apply SCC based on coding tools, it's very efficient. So that's why when you actually notice the promotion of AV2, when AOM announces new codec, they specifically mention 4 features. And there's one feature they mentioned that AV2 specifically enhance the screen coding content coding tools, because that tool is very efficient. Because of that, when we active for this machine oriented coding, like say what we do the securities, for example, autonomous cars, what you really care, you care about plates, care about ear, care about signals, care about signs, and those contents actually can, while falling into the screen content, you use the screen content coding tools, actually can encode those regions to a very low bit rate. So basically, I just want to mention that for computer vision, there's analysis that actually can help the efficient video coding, and also on the other side, the codec standard evolving into the way that further facilitate for the AI model to actually more efficient to take this video content. And then for the next part, actually, I just want to mention that if you identify those regions in this autonomous car, you can actually encode the video to actually smaller size. So this is actually the second part. Suppose there is a middle size and actually index slide. I want to talk about the second part. Second part is because now a lot of videos are being fed into the large models. I think just now when we heard from the panels, a lot of people already use that. So there's one of the many use cases, video understanding. So understanding meaning that you actually have a given video. Let's say it's a 15 minutes, actually long form video. You feed into the AI models, then you get some prompt where you can call that query. So based on the query, for example, if you ask M&E, you have a videos, you can say, okay, can you identify this actor? Can you identify those contents actually played by this actor? Or can you identify there's a car accident in this given video? It's in the autonomous cars. So for this part, you actually feed a big video content into the large model and letting the model process it. We all know that this is actually the current video understanding problem, and it takes a lot of tokens. It's actually a lot of compute. So the question will be, out of all these formats, everybody talking about the LMM is a large multimodal model, and then video is definitely the large format that actually use a lot of tokens. So can we do like token compression? On this side, you can see there's still a common thing between video token compression and bitrate compression, because we try to remove those redundancy that may not be needed to be observed by the large model. So nowadays, I mentioned this work. This is actually Storm. Actually, it's also because I mentioned NVIDIA previously. This is the second part, because they actually have a paper addressed a work called Storm. And then I mentioned this because they actually, when the large model process videos before, they actually treat videos simply as a sequence of images. We'll know that for videos, they actually, you can take one, for example, n by n, where it's actually rectangular part as one token. So then frame by frame, this is just a token representation of the video and fed into large models. So you can think that a given 15 minute long video that's actually corresponding to a lot of tokens, not alone about the audio part. And then this is actually the first time that actually token combine both spatial and temporal info. So they actually change the representation of the fed-in videos and then propose a new way to represent a sort of like a new way for the video represented by tokens. For this actual method, you actually have to change the model. Because of this, you actually have to do something retraining. So this is actually model-based token compression. Because it's a new way of representation, it's actually achieve a large amount of token efficiency improvement for processing video to implement the same video understanding work. And then, so I mentioned this is actually mentioned that for this type of work, you actually change the model, you have to retrain the models. And then there's another part of work, especially on the left side. It's actually my idea, but actually it's AI journey. It's very good to actually, there's a two part. The second part is still similar approach. You actually change the cohort representation, you represent the video in the different ways, and then you have to train the model to learn these new different ways. So this is type of approach to actually optimize the large models, but you have to retrain it. And then there's also actually train-free approaches on the left side. This is also similar for the first part I just mentioned that you actually process the videos in a certain way, you can also reduce the tokens to a large amount. For example, you fit into a 1080p videos into that, but not every frame needs to be in that resolution. Maybe you can actually use a lot smaller resolutions, convert to a large small amount of video tokens is good enough. So it actually leads to several things. You can do frame selection. You can actually reduce the resolution. You can also actually remove the duplicate frames. So for example, if I take a video of our audience and fit into that, say what are people doing, it's very obvious. You just fit one word together with the audio info, you immediately say, okay, so everybody's trying to listen to somebody like me giving a presentation. So that info is good enough. So there's a lot of things you can actually do. This is first stage. And this stage, of course, you can still use AI model, but you don't have to use the large models. You can use the lightweight models to actually process video to actually shrink a lot of info that is not related to the queries. So then this is a two method that you can achieve token compression to actually remove the redundancy. The first part is actually remove the redundancy using actually a pre-processing stage, which is a decoupled sort of large model. So this is training free. The second part is actually you have to change the model. So you have to yearly retrain the models. And then because of that, so there's quite some things we can do to actually remove the redundancy when feeding the video into large models to save token and save the processing time. And this is also one part that we have been doing. And we propose this is actually, you can look at that. For video understanding, usually the input is a pair. Once given the video, so now on the top, you have to input the video. Another thing, you have to actually input the prompt, which is your query. So now you can see that this is user query. Now you can see two lines. First, your processed video is actually exactly encoding certain part of pre-processing and then the model absorbing that. So usually, for example, if you actually input a 15 minutes long, it's already regarded as a long form. You may use different processing ways to actually chunk this video in different segments if you can detect actually some transition. So we all know that, for example, for the traditional video compression, you can actually identify the scene change, where you actually previously insert iframe. You can use a similar ways, but now you also have audios. And finally, you actually segment the given video into multiple smaller segments and letting each segment to be absorbed by the large model to actually output the content or metadata based on the queries. On the other side, the traditional ways is actually for each segment, you can generate embeddings. So this is the current way, embedding to my previous knowledge, because all these things is also new things for the past 2 years for me to learn. I take the embedding just like a hash table. It's just like string information representing that type of that segment. And on the other side, if you have a query, actually you can also generate embeddings. And then in the end, based on the query, you can actually search for the embeddings of the videos, and each video segment suppose already timestamped, that you can rank the correlations between the video embeddings as well as together matching the user queries embedding. You can actually search related content and finally output the metadata. So this is one type of work, but you can see that I outline this work. You can see this is actually query independent of the process of the video. And then the next part, I want to highlight one work. Before that, this is actually talking about the different use cases for video understanding. For example, we'll talk about OTTs, and then there's e-commerce. It's very interesting that we're working with one customer. They're actually doing e-commerce because they're actually running a e-commerce or like a online selling short video app, and then they already use video generation to actually create videos, but then they also have a lot of creators. So the reason they want to do video understanding is they want to attract the metadata together with their platform for the short video. They know that which video actually incur more user engagement. They want to actually find out the ingredient of each video that is actually related to the user engagement, and based on this, they can actually take this feedback to their creators to let the creators say, hey, what kind of video you actually include in your clip that actually potentially can sell more. So this part is also include the video understanding for them to actually extract those ingredients. And now, of course, autonomous vehicles, sports, all actually related to video understanding. This is just a different use cases. And then based on that, this is actually our current cloud offering, because for each video you can segment it into different segments. You can actually process in parallel. And then the reason actually internally we like this because this is actually very similar to our cloud vault encoding architecture. So this is a different way we can see different problems actually share the same insight. But then for the next part, I have 3 more slides, mainly talk about a specific pre-processing. It's called frame selection for actually saving or compress tokens allowed before fed into the large models. So definitely this is falling into pre-processing of the videos, and the training-free work is actually, I added particularly in my newer version that this is a work actually published by, they actually already, I can share that later on. They actually were published in CVPR early this year. They also are definitely in the archive that you can download. So that work is actually referred as a DIG, D-I-G. So the main idea of that is when you have a query, you can first classify this query into 2 types of queries. One is a global query. The other is a localized query. So what they mentioned that if you actually justify the query is a global query, for any given video, you can do the unified sampling. For example, you can choose 1 frame out of 1 second for any given video. And then you feed into this, and then to address that global query, this is good enough. You do not need to do any intelligent frame selection. However, if you actually classified the input query actually as a localized query, then there's a way that you can make the query more effective to actually identify. This is actually the main frame, but it's also already justified our own method. But you can see that this is actually the workflow of we justified. But follow this chart. I just want to see that it's actually for any given video. Just like we said, it's actually have a query. If you actually include that query into the frame selection process, that means for each specific query, you can select a number of frames, even a 15 minutes long video. If you actually identify this query is a localized query, you can select a very limited number of frames, like 32, 64, or 128. As long as you actually include the specific query into your frame selection process. This is a fundamental idea. Then you actually generate that frames. For example, a 15-minute, you just actually single out 30 frames out of all these 15-minute video, and then you use the selected images, 32 images, fed into large model to actually generate the final metadata. And you will see that it's very efficient. And here is the result from our benchmarking. So in this result, you can see that is, this is actually, I just use this slide then. And you can see source video, meaning that you just feed the original video into the large model. And it actually specified into two sets. So one set is actually sort of, you can think about, it's sort of there's some fine tuning. And the second set, independent set, is actually has nothing to do with any fine tuning based on the query specific token compressive path. So you can see that if you feed into the source video, that is the second column. If you use a compressed input, just 32 frames. And then based on the result, you can see that overall the efficiency or the accuracy just dropped by 6%. So this is a drop of the accuracy for this experiment. This is on top of it's called the video LM. Is actually this set. I already got the new version. It's a video MME. So it's a special set, special mark, and they have a query. Each query is a question, and each question has four multiple choices, and one of the choices is correct. So let's use that to actually benchmark how accuracy your result of for video understanding is. And then the compressed video is actually show that it's less accuracy by 6 point plus, but it's actually have a large compressions. This is token parameter, meaning that the final tokens that actually used by the amount only 25%. Actually, the new result is a lot better than this. It's actually lower, still similar points, but actually achieve 85% token compression. That's our new result. And that means that almost one level. For example, you can use 8 to 10 X less tokens to actually implement very similar video understanding job. Because of this, you can see that when you efficiently remove the redundancy of the input video only as a training-free per-processing state, you can actually largely reduce the tokens and then therefore largely improve the token efficiency as well as the processing time for video understanding job. So this is one of the work which is named as frame or query-aware frame selection method. So based on this two part, you can see that the video redundancy, if you actually smartly find a way, you can actually save the bits, and then now you can save the tokens now. So that's actually conclude my work. Thank you.